Good morning, students. This is your sir, SNB sir. You will be knowing the present situation that we are facing in India and all over the globe. Please be careful, stay at home, don't go outside. Enjoy with your parents, with your brothers, sisters. When you felt bored, please listen to these videos so that you will be able to cope up with the subject. So, I will be starting a new chapter, that is moving charges and magnetism, for you today. So, here we are discussing the relationship between electricity, magnetism, which is called as electromagnetic induction. 2000 years before, we know that electricity is there and even magnetism is also there, but they are dealt as a different topics. But 200 years before, that is in 1820, a famous scientist named as Hans Christian Ørsted, when he is giving a lecture demonstration for his students, he noticed that when a current carrying conductor is there, a magnetic compass by the side of that current carrying conductor is getting deflected. Then he had a question, why this magnetic needle is getting deflected? He varied the current in the conductor by changing the direction. Then he noticed an opposite kind of deflection in the magnetic compass. Then why this is happening? This is a question that is arised in his mind. Then he made some other changes in the strength of the current as well as the distance of the magnetic compass from the current carrying conductor. What he noticed means, when the strength of current is increased, the amount of deflection in the magnetic needle is also increased. When the strength of current is decreased, then the amount of deflection in the magnetic needle is decreased. Similarly, what he did is, he made the current to pass through the conductor and he changed the distance of the magnetic compass from the current carrying conductor. He noticed that as the distance is increasing, then the amount of deflection is decreasing. So, we know that if magnet is getting deflected, then it should be under some other magnetic field, because it is just like the case in electrostatics. A charge can interact with another charge. We know that a magnetic compass is getting deflected means it must be present in the magnetic field. Then who is producing this magnetic field? Then here no other thing is there except the current carrying conductor, which says that a current carrying conductor is responsible for producing the magnetic field. Then in what way the amount of magnetic field is produced around the current carrying conductor, that we will discuss here. And in this moving charges and magnetism, first we will discuss about the magnetic force experienced by a moving charge, and then we will discuss about the magnetic force experienced by a current carrying conductor placed in the magnetic field, which will, and we will also study about the Lorentz magnetic force. Later we will study about the Biot-Savart law, and we will study the applications of those Biot-Savart law. Coming to the first one, that is, if there is a charge q, around the charge there is an electric field, as we studied in electrostatics. If this is a charge, this charge is surrounded by an electric field. In the similar way, if there is a magnet, around this magnet there will be magnetic field. There will be magnetic field around this magnet. Around the charge there is an electric field. Around the magnet there is a magnetic field. If there is an interaction in the sense the force that is acting between the two bodies. Interaction is in physics is nothing but the force that is acting. So, if one charge is interacted with another charge, then for this interaction to take place, then there should be something that is responsible for that interaction. Then what is that something here responsible for the interaction? What is that something is nothing but the exchange of photons. The electrostatic forces are responsible because of the exchange of photons. In the similar way, if a magnet is interacting with another magnetic material, then what is responsible? Particle here. So, when a magnet is interacting with another magnetic particle or another magnetic material, then the interacting particles are nothing but, once again, they are nothing but the photons. Then, for electrostatic force as well as for the magnetic force, the interacting particles are nothing but the photons. Photons are responsible for interactions, electromagnetic interactions. I have told you that just 200 years before only we came to know that electricity is not a different aspect and magnetism is not a different aspect. Both are put together, we can study as electromagnetic induction. So, nowadays we are not separating electricity from magnetism, they are just like the two faces of a coin. If you are studying about electricity, indirectly we are also studying about the magnetism also. They are just like the two faces of a coin. So nowadays we are treating it electricity and magnetism as electromagnetic induction. This unification was done by Maxwell. Maxwell is the scientist who has unified electricity and magnetism. Then while he is unifying, he also noticed that even optics also comes under this electricity and magnetism, and we are learning it as electromagnetic wave theory. Here Maxwell is the one who has proposed the electromagnetic wave theory, and he has unified electricity, magnetism and optics as a single subject. So now we will be studying about how the magnetic force is acting on a charge. Suppose there is a charge Q, and this charge Q is moving in a particular direction with velocity v. If this magnetic charge is moving in a magnetic field B, let me choose, this is the representation of magnetic field. Here the charge Q is moving with velocity v, in this direction, whereas there is a uniform magnetic field directed in this way. Now the charge is moving at an angle theta with the field direction. Then what is the amount of force acting on the magnetic force acting on the charge is the question here. The amount of magnetic force acting on the charge is given by the formula F bar is equal to Q into V bar cross B bar. This is the vectorial representation of magnetic force acting on the moving charge. Then on what parameters does this magnetic force will depend? The magnetic force acting on the charge will depend upon the strength of the charge, it is depending upon the velocity of the charged particle, and it is also depending upon the magnetic field, and it is also depending upon the directions in which the velocity and magnetic field are acting. We will study the different cases so that we will understand the magnetic force properly. Case 1, if the charge on the body is 0 and the body is kept in the uniform magnetic field, then what is the magnetic force acting on it? If Q is equal to 0, then what is the magnetic force? If Q is equal to 0, Q being 0, 0 into something will be 0, therefore the magnetic force is equal to 0. So mathematically I can say that when the charge on the body is 0 and it is present in the magnetic field, then the magnetic force acting on it is 0. But why the magnetic force acting on it is 0? For that we can study theoretically also, that is, as I told you that when two particles are interacting, then the two particles fields must be same. That means if a duster is interacted with a piece of chalk, here the interaction is because of the gravitational force. For the gravitational interaction, one body should be present in the gravitational field of another body. If this is in the gravitational field of this, or this is in the gravitational field of this piece of chalk, then there will be a gravitational interaction. Similarly, if a magnetic material is present in the another magnetic field, then it will be having a magnetic force. If a charge is present in the electric field of another charge, then it will be experiencing the electric force. Then here, if a charge Q is at rest, then it is having the ability to produce only the electric field. A charge at rest will produce only electric field. Then it will produce only electric field. So here, if Q is equal to 0, that means if the charge on a body is 0, then as there is no charge on the body, then there is no electric field. Similarly, if as there is no charge on the body, there won't be any magnetic field also. Now, but there is a charge on a body, that body is having some specific mass. Because of that specific mass, it will have the gravitational field. And here, gravitational field cannot interact with the magnetic field directly. Therefore, there won't be any kind of magnetic force acting on this charge. But in case 2, if charge is at rest, this is the charge is at rest, then it will produce only electric field. Now, a charge at rest, a charge simply kept in the uniform magnetic field at rest. So Q is stationary, A stationary charge can produce only electric field, it cannot produce a magnetic field. Here electric field is there and magnetic field is there. They cannot interact directly, therefore the magnetic force acting on the charge which is at rest is 0. Therefore, or else I can say mathematically as if Q is at rest, then V is equal to 0, implies FB is equal to Q into V bar cross B bar. This implies F bar is equal to Q into 0 bar cross B bar, which says that magnetic force is 0. This is a mathematical way of explaining why the magnetic force on the charge at rest is 0. And theoretically we can say that if the charge is at rest, it can produce only the electric field, and electric field cannot interact directly with the magnetic field. So therefore magnetic force on it is 0. Next, case 3. Case 3. Let me write here. We know that magnetic force is equal to Q into V bar cross B bar. Now in case 3, when there is no magnetic field, then magnetic force on it is 0. When B is equal to 0, then the magnetic force is also 0. And lastly, this can also be written as FB in vector form, we are writing it as Q into V bar cross B bar, or I can write it as FB bar is equal to Q into V into B into sine theta into n cap. So here left side term is a vector quantity, therefore right side term must be a vector quantity. Therefore, here BQV sin theta represents the strength of the magnetic force, while this n cap is a unit vector which is directed in the direction of the magnetic force. So n cap is a unit vector directed in the direction of magnetic force, and this will give the strength of the magnetic force. Now from this, what is this theta here? Theta is the angle between the V bar and B bar. The angle between velocity vector of the charged particle and the magnetic field is nothing but the theta. So as I have drawn previously, if this is the magnetic field B bar and charge is directed in this way with velocity V bar, and theta is the angle between V bar and B bar, and Q is the charge that is moving with velocity V, then magnetic force is given by BQV sin theta, or else I can write it as FB bar is equal to BQV sin theta into n cap. Here n cap is the direction of the magnetic force. Then how to get the direction of the magnetic force here? To get the direction of magnetic force acting on the charge, it is very simple. We have to go for the curl rule. What the curl rule says means we have to take our right hand and we have to move the right hand from the first vector towards the second vector. In this one, the first vector is velocity vector and second vector is magnetic field vector. Let me turn my right hand fingers from first vector velocity vector towards the second vector, that is magnetic field vector. Then thumb will give the direction of V bar cross V bar. So here if I move my fingers from V to B, the thumb is directed into the board. The thumb is directed into the board and this thumb will give the direction of the magnetic force. Therefore, the direction of n cap is directed into the board in this case. Let me take another example to find the direction of the magnetic force. Suppose the magnetic field is directed in this is the velocity vector direction and this is the magnetic field direction. That means a charge Q is moving along this direction, whereas the magnetic field is directed downward. Then what is the direction of magnetic force? Again I am using the curl rule. Just curl your fingers of right hand from the first vector towards the second vector. It is directed into the board. In physics, any physical quantity that is directed into the board is represented by an encircled into like this. And a physical quantity which is coming out of the board is indicated with encircled dot. The encircled dot says that the physical quantity is coming out of the board, and the encircled cross will indicate the physical quantity is going into the board. If I have written like this, what it says? Here F stands for force. The physical quantity is force and into says that the force is directed into the board. If I have written like this, Here the physical quantity is the force and it is directed out of the board. So, as it is a 3-dimensional case, we cannot show the 3-dimensional case on a 2-dimensional plane. What we are doing means we are taking the advantage of these two, encircle dot and encircle into. Encircle dot says that the physical quantity is coming out of the board, whereas the encircle into says that the physical quantity is going into the board. Now, according to this, the direction of force is given like this: V bar cross B bar is directed into the board. So, the direction of unit vector is directed into the board. Simply I can draw like this with F like this. It says that force is directed into the board. Let me take another example. This is velocity vector direction and this is magnetic field direction. What is the direction of magnetic force? I have to turn my fingers from the first vector towards the second vector. Here the first vector is velocity vector and second vector is magnetic field vector. Here the magnetic force is directed out of the board. Therefore, something which is coming out is indicated with the encircled dot, and I have to indicate like this. This says that the force is directed out of the board. Is it clear? Now, in this way, using the curl rule, we can find the direction of the magnetic force. This will give the strength. BQV sin theta will give the strength of the magnetic force acting on this moving charge, whereas n cap will give the direction of that magnetic force. So now, using this formula, which is important for all kinds of examination, we will study some special cases. Special cases. If the charge is moving in the direction of magnetic field, what will be the magnetic force acting on it? If the charge Q is moving in the direction of magnetic field, what is the direction of magnetic force acting on it? What is the angle between the velocity vector and magnetic field here? Here the angle between velocity vector and magnetic field is theta is equal to 0 because they are parallel to each other. Once theta is 0, then the magnetic force is given by Fb is equal to BQV sin theta, which says that this is BQV sin 0. Sin 0 value is 0, therefore BQV into 0, which is equal to 0. In the similar way, if the charge is moving anti-parallel to the direction of magnetic field, this is the direction of magnetic field, let me take, and the charge Q is moving in this direction. This is the velocity vector direction and this is magnetic field direction. Then what is the magnetic force acting on the charged particle? Here, velocity vector and magnetic field vector are anti-parallel to each other, therefore theta is equal to 180 degrees. Theta being 180, sin 180 is equal to 0, therefore magnetic force is equal to 0. So, finally what we can conclude here means this is F is equal to BQV sin 180, which is equal to 0 because sin 180 is equal to 0, which says that the magnetic force is 0 if the charge is under motion also, but under which conditions? When the charge moves either parallel to the direction of magnetic field or when the charge moves anti-parallel to the direction of magnetic field. In both the cases, what might be the magnitude of the charge, the magnetic force acting on it is 0. So, the important point that we have to notice here is, even though the charge is under motion, the magnetic force acting on the charge will be 0 provided the charge is moving either parallel to the magnetic field or anti-parallel to the magnetic field. Next, second case, case 2. What will happen if the charge moves perpendicular to the direction of magnetic field? Let me take, this is the direction of magnetic field. Uniform magnetic field is directed towards right side, and here a charge Q is there and the charge it is directed upward. So, in this direction it is moving. So, what is the angle between velocity vector and magnetic field in this case? The angle between these two is theta is equal to 90 degrees. As theta is equal to 90 degrees, what will be the magnetic force acting on it? Fb is equal to, F bar is equal to BQV into sin theta into n cap. That is equal to BQV into sin 90 degrees into n cap. That is equal to, sin 90 value is 1. We know that sin 90 is equal to 1. Therefore, this is equal to BQV into n cap, since sin 90 is equal to 1. Is it clear? So this is the magnetic force experienced by a charge which is moving perpendicular to the direction of magnetic field. And if you observe carefully, the magnetic force is depending upon the angle between the velocity vector and the magnetic field vector. If the angle changes without any change in the charge, without any change in the velocity, magnitude of velocity and magnetic field, if theta changes, then the magnetic force is going to be changed. When does this magnetic force is maximum and when does this magnetic force is minimum is the question here. That completely depends upon the angle theta here. If theta is sin theta, we know that sin theta always lies between plus 1 and minus 1. As we know this concept, sin theta always lies between minus 1 and plus 1. So this force will be maximum when sin theta is maximum. The sin theta is maximum for plus 1. That means when theta is equal to 90 degrees, we will have a maximum value. Therefore, the magnetic force will be maximum when the charge moves perpendicular to the field direction, magnetic field direction. So this is the maximum magnetic force acting on the charged particle. If a charged particle moves perpendicular to the direction of magnetic field, then it will experience the maximum magnetic force. So they may ask a question, when does the charge will experience the maximum value of magnetic force? The answer is when it moves perpendicular to the direction of magnetic field, then it will experience the maximum magnetic force. Then in this case, what is the direction of the magnetic force acting on it? Again, we have to go for the curl rule. Velocity vector is directed upward, magnetic field is directed like this. Therefore, curl your fingers from velocity vector towards the magnetic field. Then the thumb is directed into the board. So therefore, the direction of n cap is directed into the board. Is it clear? This is about the magnetic force acting on a charged particle moving in the magnetic field. Is it clear? The next topic is the force acting on the charged conductor placed in a uniform magnetic field. Suppose there is a current carrying conductor carrying a current of I amperes. Now this current carrying conductor is placed in a uniform magnetic field. It is placed in a uniform magnetic field. A uniform magnetic field is one whose strength is same at each and every place and its direction is also invariable. If the direction does not changes from point to point and the strength of the field remains same at each and every point, then we will say that the magnetic field is uniform. So here there is a current carrying conductor carrying a current of I amperes. Let the length of this current carrying conductor is equal to L, carrying a current of I amperes, and this conductor is kept at an angle of theta with the field direction. Then what is the magnetic force acting on this current carrying conductor? The magnetic force acting on this current carrying conductor is given by F bar is equal to I into L bar cross B bar. So here we know that the left hand side term, that is force, is a vector quantity. Current I is a scalar quantity here. Therefore, if left hand side is a vector, then right hand side must be a vector. Therefore, here L bar cross B bar represents a vector quantity. B bar being vector, current being scalar, then we need to take another quantity which is vector. Here we are choosing L, that is length, as a vector physical quantity. Generally length is a scalar, but here for small elemental parts we will be treating the length as a vector quantity. More clearly we will be calling it as current element. I into L is said to be the vector quantity here, current element. So this is the actual formula that we have to derive for the magnetic force acting on a current carrying conductor placed in the uniform magnetic field. It can also be written like this: F bar is equal to BIL into sin theta into n cap. So here, according to the mathematics, A bar cross B bar can be written as A into B into sin theta into n cap. Here A is a vector and B is a vector. Theta is the angle between A bar and B bar. Similarly, if A bar cross B bar is equal to AB sin theta into n cap according to mathematics, in the similar way L bar cross B bar can be written as L into B into sin theta, where theta is the angle between L bar and B bar. So now what is this n cap means? N cap is the direction of force, or it is a unit vector directed in the direction of magnetic force. Then this BIL sin theta represents what here? This BIL sin theta represents the strength of the magnetic force acting on the current carrying conductor. How to get this formula means, by using the previous analogy, we can get this formula easily. Let us consider there is a current carrying conductor of length L. There is a current carrying conductor of length L having uniform cross sectional area A. A is a uniform cross sectional area. Let there are small n number of charges per unit volume of this conductor. So here small n indicates the number of charges per unit volume, or charge density I can say. N is the charge density. Charge density, which means the number of charges per unit volume. I can also write it as N is equal to number of charges divided by volume, which can be written as N is equal to capital N, where capital N stands for the number of charges. Volume of the conductor is nothing but area of cross section into length. This implies number of charges is equal to number of charges, N is equal to small n into A into L. Now, if the charge on each one is small q, then what is the total charge of capital N number of charges? The total charge is equal to number of charges into charge on each particle. So which is equal to small n into A into L into Q. This is the total charge inside the conductor. Now if I place a conductor inside the magnetic field and the current is flowing through it, current is flowing is nothing but the charges are flowing through it. Now how much charge is flowing through it? So this is the total charge that is flowing in this direction, because charges are restricted to move along the length of the conductor in this case. Therefore, this is the total charge which is moving in this direction, making an angle theta with the field direction. If V is the velocity of those charged particles, then according to the previous idea, the magnetic force is given by F is equal to B into Q into V into sin theta into n cap. This is the magnetic force acting on the moving charges. Here moving charges are, how much is the moving charge here? This is the charge that is moving. Therefore, I can write it as B is the magnetic field in which the conductor is placed. B is the magnetic field in which the conductor is placed. Q means the total charge, which is equal to N into A into L into small q. Small q being the charge on each particle. And in this conductor, how many number of charges are there means capital N charges are there. Therefore, I can write it as total number of charges is N into small q, that is equal to this value. So the total charge that is present in the magnetic field is nothing but small n into A into L into Q into V into sin theta into n cap. Then how to write this one here? So here this term N into A into L into Q represents the total charge. V is the velocity with which the charges are moving. But we know that current I is equal to charge by time, or net charge by time. So here net charge is this value. So net charge can also be written as current into time. Therefore, I can write it as B into I into T into V into sin theta into n cap. So this implies velocity is nothing but distance by time. So I can write it as B into I into T into L by T into sin theta into n cap. This implies T will cancel, then I will be having BIL into sin theta into n cap. This is how we will be knowing that the force acting on a current carrying conductor is written as BIL sin theta or BIL sin theta, and here this BIL sin theta represents magnitude or the strength of the magnetic force acting on the current carrying conductor placed in the uniform magnetic field. Just like the previous case, here also we will be having the special cases when the conductor is placed in the direction of magnetic field. or anti-parallel to the direction of magnetic field. That is, for theta is equal to 0 degrees or theta is equal to 180 degrees, the magnetic force acting on the conductor is equal to BIL into 0 into n cap, because sin 0 is 0 and sin 180 is also 0. Therefore, the magnetic force acting on the conductor is 0, which says that when a conductor is placed, current carrying conductor is placed either parallel to the magnetic field or anti-parallel to the magnetic field, then the net magnetic force on it is 0. If this is the direction of magnetic field and this is the current carrying conductor, here theta is equal to 0 and there is no magnetic force acting on it. Now, when does the current carrying conductor placed in magnetic field will experience the maximum magnetic force? This is an important one. When the conductor is kept like this, that is kept perpendicular to the field direction. When the current carrying conductor is kept perpendicular to the field direction, then the magnetic force acting on it is nothing but BIL into sine 90 degrees into n cap. Sine 90 is maximum value of sine theta, that is equal to 1. Therefore, BIL into 1 into n cap. This is equal to BIL into n cap. This is the magnetic force. Therefore, I can say F maximum is equal to BIL. So, a current carrying conductor will experience a maximum magnetic force when it is kept perpendicular to the field direction. So, what is the important things that we have to notice is, when the current carrying conductor is placed perpendicular to the direction of magnetic field, then it is going to experience the maximum value of magnetic force. When it is parallel or anti-parallel to the field direction, then it will experience a 0 magnetic force. It is similar to the case where a charge is moving parallel to the magnetic field or anti-parallel to the magnetic field, it is experiencing the 0 magnetic force. And when the charge is moving perpendicular to the direction of magnetic field, it is experiencing the maximum magnetic force. In the same way, we are having here also. So, the conductor is experiencing the maximum magnetic force, that is equal to BIL when it is placed perpendicular to the direction of magnetic field. So, here the vector notation for the force is represented like this. L bar cross B bar is the one which is giving the direction for the magnetic force. Generally, length is a scalar physical quantity, but here we are taking, for small elemental lengths, we are treating it as a vector physical quantity. Here current is scalar, magnetic field is vector, length is a scalar, but the current element, that is I into dl, small current element, is taken as a vector quantity. Why we need to take means, if left hand side is a vector, then right hand side term must be vector. In order to satisfy that, we are taking L bar as a vector physical quantity here. Is it clear? Now, the direction of magnetic force is obtained simply by using the right hand curl rule. Curl your fingers from the L bar direction to the B bar direction. So, the direction of magnetic force here will be directed into the board. Is it clear? Next. The next topic is Lorentz magnetic force. Lorentz is the name of the scientist who has established this Lorentz magnetic force formula. We know that previously, if a charge Q is placed in an electric field E, if there is a charge Q placed in electric field E, then it is going to experience an electric force which is given by F bar is equal to E bar into Q. This is the formula for electric force experienced by a charge placed in electric field, which we studied in the electrostatics part. This is the electric force. So, now a charge is present in an electric field E, then it is experiencing an electric force. F is equal to E bar into Q. I will be taking it as F small e. This is electrical force. In the similar way, if a charge Q is placed in a magnetic field, if a charge Q is moving with velocity V bar and it is kept in a uniform magnetic field B bar, then what is the magnetic force experienced by it? The magnetic force experienced by it is given by, already we studied that FB bar is equal to Q into V bar cross B bar. Now, if suppose charge is not present alone in the electric field or not present alone in the magnetic field, If it is present in the combined electric and magnetic field, what is the net magnetic force experienced by it? If a charge is present in the combined electric and magnetic field, then what is the net force experienced by it? It can be obtained using the superposition principle. Here this is the electrical force when it is in the electric field, and it is the magnetic force when it is in the magnetic field. Therefore, the net magnetic force experienced by the charge, present in combined electric and magnetic field, is given by superposition principle. That is, net force is equal to the electrical force Fe bar plus magnetic force Fb bar. So according to this, I can write it as F bar is equal to E bar into Q plus Q into V bar cross B bar. This is the net electric force and magnetic force, or the net force experienced by the charge present in the combined electric and magnetic field. And this force is termed as Lorentz force. This entire term is called as Lorentz force. I can also write it as F bar is equal to Q into E bar plus V bar cross B bar. Here we are taking Q common and it is written outside. Then I can write it as F bar is equal to Q into E bar plus V bar cross B bar. The direction of Lorentz force will be the direction of E bar plus V bar cross B bar, provided Q is positive charge. If Q is positive charge, then the direction of the Lorentz force is nothing but the direction of E bar plus V bar cross B bar. If Q is a negative charge, then the direction of Lorentz force is opposite to the direction of E bar plus V bar cross B bar. Is it clear? So based on the polarity of the charge, the direction of force is going to be affected. Similarly here also, the direction of magnetic force is the direction of V bar cross B bar. If Q is positive, then F bar direction is the direction of V bar cross B bar. If Q is negative, then the direction of F bar is nothing but the direction opposite to V bar cross and B bar. If Q is negative, then F bar direction is opposite to the direction of V bar cross B bar. Is it clear? This is one of the important point. Many times we have to use this in competitive part of examination. If Q is positive, then the direction of magnetic force is nothing but the direction of V bar cross B bar. If Q is negative, the direction of magnetic force is opposite to the direction of V bar and V bar cross B bar. And here also, Q being positive, the direction of electric force is the direction of electric field. If Q is negative, the direction of F bar is opposite to the electric field direction. For example, let us consider here this is a plus 3 nanocoulomb charge and electric field is directed towards positive x-axis. What is the direction of electric force? Here Q is plus 3 nanocoulomb I told, so it is a positive charge. Electric field is directed along the x-axis I told, therefore the direction of electric force will be the direction of electric field, so that force direction is along positive x-axis. If suppose if it is negative charge, that is minus 3 nanocoulomb, and if E bar is directed along positive x-axis, then F bar should be directed opposite to the positive x direction, that is along negative x direction. Is it clear? So Q being positive, the directions will be in the direction of the net field. Q being negative, directions will be opposite to the net field direction. Is it clear? So this is called as the Lorentz force, and this is said to be the Lorentz magnetic force, while this is said to be the Lorentz electric force. Sometimes in the board examination they will be asking for 2 marks, write the formula for Lorentz magnetic force, then we have to write only this part. Lorentz electric force, only this part. If simply they ask to write the formula for Lorentz force, we have to write this formula. This is called Lorentz force, which was specified by scientist named Lorentz. This is Lorentz magnetic force and this is Lorentz electric force. So, the net force experienced by the charge in the combined electric and magnetic field is said to be the Lorentz force. Is it clear? And based on this formula, there is Lorentz force formula, a velocity selector condition is established, which will be used in the many devices like cyclotron and other accelerators. Is it clear? We will discuss about the cyclotron and other cases in the next topic. Next is velocity selector condition. This velocity selector condition will be based on the Lorentz force. As we discussed in the previous topic, Lorentz force is nothing but the net magnetic force experienced by the electric field and the magnetic field. Let me choose the Lorentz force formula as F bar is equal to Q into E bar plus V bar cross B bar. This is the formula for Lorentz force when a charge is moving in the combined electric and magnetic field. Suppose the Lorentz force is 0, then what is going to happen? If the Lorentz force is 0, then F bar being 0, we have 0 bar is equal to Q into E bar plus V bar cross B bar. This implies that Q cannot be 0, therefore, E bar plus V bar cross B bar is equal to 0 bar. This implies E bar is equal to minus of V bar cross B bar. What it says? If the direction of electric field is in the direction opposite to V bar cross B bar, then we will be having the, if the strength of electric field is equal to the strength of V bar cross V bar and its direction is opposite to V bar cross V bar, then net force will be 0. For that, I will give you one graphical explanation here. Let me choose, this is x axis, this is y axis and this is z axis. Let us consider a charge q is moving in this direction with velocity v bar. So, now I am extending it like this, this is the y axis and this is the z axis. So, this is v bar. Now, this is, let me take it as E bar. This is E bar and this is B bar. So, here velocity vector, electric field vector and magnetic field vector, all the three are mutually perpendicular to each other. Velocity vector is perpendicular to electric field vector and it is also perpendicular to the magnetic field vector. Similarly, electric field is perpendicular to velocity vector and it is also perpendicular to magnetic field vector. So, here all the three variables, that is velocity vector, electric field vector and magnetic field vector, are mutually perpendicular to each other. If they are mutually perpendicular to each other, how the force's direction will be? Now, let us take, for simplicity, Q is a positive charge. If Q is a positive charge which is moving like this, electric field is directed in this way, then the direction of electric force must be, Q being positive charge, the direction of electric force is nothing but the direction of electric field. Therefore, this will be the direction of electrical force, Fe bar is directed upward. Now, what is the direction of magnetic force acting on this charge? Direction of magnetic force is nothing but direction of V bar cross B bar if Q being positive. V bar is along x axis and this is along, this is y axis we are having, this is x axis, z axis will be like this. Therefore, if I turn like this, this is y axis, this is x axis, then this is going to represent the z axis, x, y, z. Now, what is the direction of V bar cross B bar? V bar cross B bar is like this. So, directed along the negative y direction. Is it clear? This is z axis, this is x axis, V bar is like this, B bar is like this. Direction of V bar cross B bar is V to B, directed downward. Therefore, the direction of the magnetic force is like this. This is the direction of magnetic force. Now, when the magnitude of electric force is equal to the magnetic force is equal to the magnitude of magnetic force, then then two forces will cancel each other, net force on the charge will be 0. Once the net force is 0, how the charged particle is going to move? If the net force is 0, it will travel undeviated, and it is said to be the velocity selector condition. What the velocity selector condition says means, if a charged particle entering into the combined electric and magnetic field travels undeviated, ಯಾವುದಾದ್ರೂ ಒಂದು ಚಾರ್ಜ್ ಅನ್ನೋದು ಕಂಬೈನ್ಡ್ ಎಲೆಕ್ಟ್ರಿಕ್ ಅಂಡ್ ಮತ್ತು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡಲ್ಲಿ ಹೋಗುವಾಗ ಅದರ ದಾರಿ ಚೇಂಜ್ ಆಗ್ದಂಗೆ ಹೋಗ್ತಾ ಇದ್ದರೆ ವಿಲ್ ಕಾಲ್ ಇಟ್ ಆಸ್ ಅನ್ಡಿವಿಯೇಟೆಡ್ ಆರ್ ವೆಲಾಸಿಟಿ ಸೆಲೆಕ್ಟರ್ ಕಂಡೀಷನ್. ಇಫ್ ಎ ಚಾರ್ಜ್ ಪಾರ್ಟಿಕಲ್ ಟ್ರಾವೆಲ್ಸ್ ಅನ್ಡಿವಿಯೇಟೆಡ್ in the presence of combined electric and magnetic field, then it is said to be the velocity selector condition. Now, therefore, I can conclude that for velocity selector case, Fe bar magnitude must be equal to Fb bar magnitude. This implies EQ should be equal to BQV. Here sin theta I am not taking. Why sin theta I am not taking means angle between velocity vector and magnetic field vector is 90 degrees. Sin 90 is equal to 1. We know that Fb is equal to BQV sin theta in terms of magnitude. In this case, theta is the angle between velocity vector and magnetic field vector, and that angle is equal to 90, sin 90 is equal to 1, therefore Fb is equal to BQV. Hence, EQ is equal to BQV. This implies QQ will get cancelled, then we will be having V is equal to E divided by B. V is equal to E by B. This is called velocity selector condition. When a charged particle enters into the combined electric and magnetic field, and it travels undeviated, then it is said to be the velocity selector condition. Or if I know the electric field and magnetic field, then I can find the velocity with which the charge has to move so that it travels undeviated. So here, if you observe here, electric field and magnetic field are perpendicular to each other. Therefore, I can say that the charged particle is moving in the crossed electric and magnetic field. I can draw the diagram like this. Let me choose, this is a capacitor, this is the positive plate of capacitor, this is negative plate of capacitor, and here the charge Q is moving like this with velocity V. As this is the positive plate of capacitor, this is negative plate of capacitor, electric field is directed from top to bottom like this. This is the direction of electric field. So, this charge will experience a force in which direction? Charge Q moving like this, electric field is downward, then it should experience the downward force, or positive charge should be attracted towards the negative plate. Therefore, this is the direction of electrical force. Because of electric force, the charge has to move the path like this. Now, this is electric force is trying to bring the charge downward. Now, I should select the magnetic field in such a way that the magnetic force is acting upward direction. Magnetic force should be upward means, this is the velocity vector, magnetic field should be directed into the board. Suppose this is the magnetic field. This is the magnetic field. I am indicating magnetic field with into. So, this is said to be the velocity selector condition case. Magnetic field B bar is directed into the board. Magnetic field is directed into the board and electric field is directed downward. These two are perpendicular to each other. So, then the two fields are said to be crossed. Crossed means perpendicular to each other. Crossed electric and magnetic field. Crossed E bar end. B bar means electric field and magnetic field are perpendicular to each other. In this case, what is the direction of magnetic force? Direction of magnetic force is obtained using this formula. V bar plus B bar direction is what? V bar is like this, magnetic field is into. Therefore, the direction of magnetic force is upward. So, magnetic force is upward, electric force is downward. This is magnetic force Fb, this is electric force Fe. Now, one force is trying to bring the charge upward and the other force is trying to bring the charge downward. When these two forces are equal in magnitude, then the net force on it is 0 and it travels straight without any deviation. This is called velocity selector condition. Then what is the condition for that charged particle to travel undeviated means it should move with a velocity equal to ratio of electric field and magnetic field. And this is true with the case of charged particles. And as I told you that Maxwell has unified electricity, magnetism and light, that is optics. Electromagnetic wave theory we will be calling Maxwell's electromagnetic wave theory. According to Maxwell's electromagnetic theory, an electromagnetic wave is nothing but what? It is a combination of electrical vector as well as a magnetic vector. Then what is the speed of electromagnetic wave means? Electromagnetic wave is an uncharged one. Therefore, what is the speed of this means? The speed of this is given by, speed of electromagnetic wave is given by C is equal to E by B. So, when a light is passing through the combined electric and magnetic fields, it is traveling undeviated. It is traveling undeviated means the speed of light should satisfy this condition. Whenever the light is moving as an electromagnetic wave, then the speed of light is given by electrical component of that electromagnetic wave divided by the magnetic component. So, this is the speed of electromagnetic wave, and this is the speed of the charged particle which travels undeviated. Is it clear? This is about the velocity selector condition, and this formula will be useful while we are solving the CET problems to JEE NEET problems. Next, where does this velocity selector condition will be useful? This velocity selector condition will be useful in the cyclotron device. Then what is a cyclotron? Cyclotron is a device which is designed in order to accelerate the charged particles like electrons, protons and ions. Why to accelerate these charged particles means, in order to study about the nuclear parameters, that is nuclear structures, the scientists wanted to bombard the heavy nucleus with the high speed charged particles or ions. Now, to increase the speed or in order to accelerate the charged particles, we require one device. The device which is required to accelerate the charged particle is nothing but cyclotron. We are having some other devices other than cyclotron like Van de Graaff generator. Nowadays, we are having so many devices in order to accelerate the charged particles. Cyclotron is one such device, and it was established in the year 1953 only. This cyclotron was designed. And in India also we are having the cyclotrons. Even we are having in Kolkata variable energy cyclotron center is there. And nowadays we are having different types of machines are there which are used to accelerate the charged particles. Now, these highly accelerated charged particles will be useful for bombarding the nucleus. If their nucleus is bombarded with these high energetic particles, then we are able to study the structures of that nucleus. That is the importance of accelerated charged particles. But to accelerate the charged particles, we require a device called as cyclotron. And this cyclotron is based on the velocity selector condition, and this was designed in the year 1934 by Lorentz and Livingston and Lorentz are the two scientists in the 1934. They have designed this cyclotron. Before studying about the cyclotron, why to study about all these things means, suppose we will be seeing in the sky when you go for the northern polar regions of the earth, in the Alaska or northern Canada, in Alaska or and northern part of Canada, these two are nearby the polar regions of the earth. In these polar regions, if you see the sky, we will be having some spectacular colors. Some colors will be dancing, like in green color and pink color, we will be having a dancing colored pattern will be there. Why these colors will be seen near the polar regions? But we are not noticing those kind of colors in the India or some other parts of the globe. We are not noticing these things. Only in the polar regions we are noticing the dancing colors like pink and green. Why that is happening means, that is because of the electric and magnetic force acting on the charged particles that are entering into the Earth's atmosphere near the polar regions. As I told you that whenever a charged particle enters into the magnetic field, it will experience a magnetic force. If it experiences a magnetic force, it is going to change its direction, but not its magnitude. It is going to change its direction. So now, when it is how it's going to change its direction, I will tell you in this topic cyclotron. Before going to the cyclotron, we'll discuss how the charge is changing its direction when it is entering into the magnetic field. So, if you want to know the answer for the question why the colors, spectacular colors will be seen in the northern and southern poles of the earth means that can be studied based on the motion of the charged particle in the combined electric and magnetic fields that we will discuss here. So, the answer will be found in this chapter. And now, before going to know about the cyclotron, let me briefly tell you how the direction of charge is going to be affected because of the magnetic force. Let me choose, this is a uniform magnetic field. Into says that the physical quantity is going into the board. Here I am taking into as the representation for uniform magnetic field. Let me choose, this is a uniform magnetic field which is directed into the board. Let me choose a charge Q which is positive, a charge Q which is positive and entering into the magnetic field perpendicularly. Now, when the charge enters into the magnetic field perpendicularly, we know that it will experience a maximum magnetic force. Yes or no? I told you that F is equal to BQV sin theta in terms of magnitude, and F maximum is equal to BQV since theta is equal to 90 degrees. For theta is equal to 90 degrees, the magnetic force will be maximum. So, here charge Q is entering into the magnetic field which is directed into the board. These two, velocity vector is perpendicular to magnetic field, therefore, it has to experience the maximum magnetic force. Now, because of this, what is going to happen for the direction of the charged particle? What is the direction of magnetic force? Direction of magnetic force is nothing but direction of V bar cross V bar, Q being positive. So, V bar is directed like this, B bar is directed into the board. V bar, B bar is into the board. Therefore, direction of magnetic force is upward. So, here its direction is like this. So, at every point if we consider, here if I consider the tangent drawn to the path followed, in first year we have studied that the tangent drawn to the path followed will give the direction of velocity. Therefore, if the particle is here, the velocity direction is like this, B bar is like this, force is like this. If the velocity vector is here, if the particle is moving, when the particle is here, the direction of velocity is tangential like this, V bar, and B bar is into the board, therefore, direction of force is like this. Therefore, at any point of this path, the force is directed to a particular point called the center. So, now the charged particle is going to follow which kind of path here? The charged particle is following the circular path. When a charged particle enters into the uniform magnetic field perpendicularly, then it must and should follow the circular path. This is one of the most important concept that we have to study. When a charged particle enters into the uniform magnetic field perpendicularly, then the path followed by the charged particle is always circular, always circular. Now, this I will take it as radius of that circular path. R represents the radius of the circular path when the charge enters into the uniform magnetic field perpendicularly. Is it clear? The magnetic force can bring only a change in the direction of velocity, but it cannot change the magnitude of velocity. So, magnetic force acting on the charge is not responsible for bringing a change in the magnitude of velocity. It can bring only a change in the direction of velocity. This is very important, that is to be noticed. That means, when a charged particle is traveling in a magnetic field, what is going to affect it means only the direction of velocity is going to change, but not the magnitude of velocity. So, magnitude remains same, only the thing is what is changing? The direction of velocity is going to be changed, but not the magnitude of velocity. Is it clear? Then, as it moves in a circular path, what is the time period of circular path here is the question. As it is moving in a circular path, for completing one circle, it has to take some time. The time taken by the particle to complete one circular path is said to be the time period by definition. By definition of time period, we know that it is the time taken by the particle to complete one circular path. Then, how much time it will take for completing one circular path? In completing one circular path, the charge has traveled how much distance here? Nothing but the circumference of the circular path. The circumference of the circular path is nothing but 2 pi r, where r being the radius. I will take the simple cases here. I want to calculate the time period of the circular path. Calculation of time period of circular path. Calculation of time period of circular path. So, how to calculate the time period means the time period capital T is defined as the time taken by the particle to complete one revolution. So, here we know that speed is equal to distance divided by time. Distance divided by time. Simple thing is speed is equal to distance by time. As it moves with the speed v, I can take v is equal to, in this case, only the direction of velocity is changing but not its magnitude. Therefore, speed v is equal to distance by time. Whenever the time is equal to time period, distance is nothing but the circumference of the circle. This is equal to circumference of circle divided by circumference of circle divided by time period. This implies v is equal to 2 pi r divided by capital T. This implies time period is equal to 2 pi r divided by v. Let me take it as equation 1. Now, if you observe it carefully, it is moving in the circular path. Whenever a charged particle enters into the uniform magnetic field normally or perpendicularly, it has to follow the circular path. But in first year we studied that when something moves in a circular path, then it must and should experience a force called centripetal force. As it is experiencing the centripetal force, who is providing that necessary centripetal force is the question. When a charged particle is entering into the magnetic field, it is following the circular path. If it moves in circular path, then it experiences centripetal force. Then who is responsible for the centripetal force means nothing but the magnetic force. So, in this case, the one that is to be remembered is the necessary centripetal force is provided by the magnetic force. Therefore, I can write it here. Here, the necessary centripetal force is provided by magnetic force. Therefore, what I can say here means centripetal force is Fc, that is equal to magnetic force Fp. Centripetal force, when a charged particle of mass m moves with speed, constant speed v in a circular path of radius r, then centripetal force is given by mv square divided by r. And here the magnetic force is nothing but bqv. Therefore, I can write it as bqv because sin theta is equal to 1, theta being 90 degrees. So, from this I can write that one v and v will get cancelled and we are remain with mv by r is equal to bq. Implies r is equal to mv divided by bq. An utmost important formula for all kinds of examination, especially for NEET and JEE exams. This formula is most important. You have to remember that radius of the circular path r is equal to mv divided by bq, where m is the mass of the charged particle, v is the speed with which the charged particle is moving, and b is the magnetic field in which it is moving, and q is the charge of the charged particle. So, when a charged particle enters into the uniform magnetic field normally, then the radius of the circular path followed is given by r is equal to mv by bq, while the time period of revolution is given by t is equal to 2 pi r by v. Now, let me take this as equation 2 and this as equation 1. Using equation 1 and equation 2, what I can say? Using equation 1 and equation 2, using equation 1 and equation 2, I can say that T is equal to 2 pi by V into, here radius is nothing but mv divided by bq. So what you are understanding here, T is equal to 2 pi r by V and r is equal to mv by bq. In the place of r, I will substitute this value. Therefore, T is equal to 2 pi by V into mv divided by bq. So V and V will get cancelled. T is equal to 2 pi divided by 2 pi m divided by bq. It is also very important formula for all kinds of examination. For board, NEET and JEE examination, this is the most important formula. So the time period of revolution of the charged particle is given by T is equal to 2 pi m by bq. What you are understanding using this formula? What we are understanding means, if I want to increase the radius of the circular path, what I need to change? In order to increase the radius of the circular path by keeping the mass and charge constant, I need to increase the speed or I need to change the magnetic field. Suppose if two charged particles having the same charge and same mass enters into the same magnetic field, then radius of the circular path is directly related with the velocity. So radius will depend upon the velocity of the charged particle. If you see the time period here, time period of revolution is independent of velocity of the charged particle, and it is one of the most important condition that is required in the cyclotron case. So if you observe this one, the time period of revolution of the charged particle is independent of the velocity of the charged particle. If a particle moves with more and more velocity, does the time period is affected? No, the time period is not affected by the velocity. Time period is affected only by the mass and charge, but it is not affected by the velocity of the charged particle. Is it clear? So time period is independent of velocity of the charged particle. Time period is affected only by the magnitude of charge and mass. Is it clear? So this is about the calculation of time period and calculation of the radius of the circular path when a charged particle enters into the uniform magnetic field normally. So conclusion is, when a charged particle enters into the uniform magnetic field, what is the path it will follow? Circular. When a charged particle enters into the uniform magnetic field, it will follow the circular path, must and should follow the circular path. Okay. In the next concept we will study what is the path it will follow when it travels at an angle other than 90 degrees. So for 90 degrees angle, it is following the circular path. If it follows the circular path, what is the radius of the circular path? R is equal to mv divided by bq. And what is the time period formula? T is equal to 2 pi m by bq. So time period of revolution is independent of velocity of the charged particle. And this will be used as a principle in the designing of cyclotron. Is it clear? About the cyclotron. The cyclotron is a device which is used to accelerate the charged particles, where the accelerated charged particles will be used further in the medical field. We can use them, and in the field of nuclear physics these will be very much useful. Why? Because for studying the structures of the nucleus we require the accelerated charges. This is a device which is designed in the year 1934 by the scientist named Lorentz and Livingston. Livingston are the two scientists who has designed this cyclotron. This cyclotron will consist of two D-shaped metallic conductors will be there. There will be two D-shaped metallic conductors will be there like this. So as the shape of this three-dimensional metallic conductor is D, we will be calling them as Ds, D-E-E-S, Ds, named as Ds. This is D1 and this is D2. So in a cyclotron there will be two Ds will be there which are made up of metals, and we have studied in electrostatics that the electric field will be shielded using the metals. Electric lines of force cannot pass through the metals. So based on that idea, in these Ds there won't be electric field. Why? Because these are made up of metals, therefore electric field lines cannot enter into this D shapes. Now between the two Ds we will leave a small gap. There is a small or a fine gap is left between the two Ds. So here these two Ds are connected to a alternating voltage source. High frequency alternating voltage source is used to connect the two Ds. The frequency of this is taken as frequency of the applied source as FA. Let us take FA as the frequency of the applied source which is connected to the 2Ds. I will tell you what is the use of this high frequency source which is connected to the Ds. In between the Ds there will be a small gap I told you, and at the center I will release a charged particle. I will release a positively charged particle for our convenience. I am releasing a positively charged particle here in between the 2Ds. Now, first we will make this as positive and this as negative at some instant. Let us consider, because of this alternating source, at some particular instant this is positively charged and this is negatively charged. Now, between the positive and negative there will be an electric field directed like this. The electric field is directed from positive plate to the negative plate. Now, if you observe here, the charge Q is present in the electric field E, then it should experience what? It should experience an electric force, and that is given by F bar is equal to E bar into Q. Q being positive and Q is there in the electric field E, it is experiencing a force in the direction of electric field. Therefore, because of this force, the charge has to be pulled into the D2 plate, D to D. Into this one, this charge is to be experiencing a force. Because of that, the charge will try to move towards right side D. When it is moving, as F is equal to ma, I can say that the charge is getting accelerated. That means, due to this electric force, the charged particle will accelerate. That means its speed is increasing. Now, it will enter into this D. Once it enter into this D with some velocity v, in this D, there will be a magnetic field. There will be a magnetic field which is into the board. Let us consider this is a magnetic field which is directed into the Ds. Now, because of this magnetic field which is directed into, previously I told you that whenever a charged particle enters into the perpendicular magnetic field, it has to follow the circular path. Now, the velocity direction is like this, magnetic field is into, therefore, it has to move upward and it has to follow. When a charged particle enters into the magnetic field, normally it has to follow the circular path. Therefore, it will follow a circle like this and it will come like this. By the time it completes half of the revolution, the polarity will be altered, that means inverted. This becomes positive, this is negative. So, what you understood here means the frequency of the applied source must be so designed such that by the time the charged particle travels inside one of the D, it has to change its polarity. So, the time period of this polarity must be equal to half of time period of this time period of revolution of this charged particle inside the D. Now, what happens? The charged particle is coming with some velocity and it is directed into this side, left side, and now the direction of electric field is reversed. Now, the electric field is directed in this way. Now, because of when the charged particle comes like this, again it is experiencing electric force in this direction. Because of that electric force, what happens? The speed will increase. Once the speed increases, we know that R is equal to mv by bq. When the speed increases, radius should also increase. Therefore, its speed goes on increases and it comes like this. When it comes like this, here the magnetic field is there again. Because of that one, it will increase its speed. Therefore, radius of the circular path increases. It will come like this. Again, when it comes here, again polarity is going to be changed, positive, negative. So, after every half cycle, the polarities will be changed on the Ds. After every half cycle of the charged particles, the polarities of the Ds must be changed that can be done with the help of the applied frequency. Now, here it comes, again the speed increases. Now, it increases like this. Because of this one, the radius of the path increases, and finally, it will come out of one of the Ds. Here there will be a deflecting plate will be there. This is called deflecting plate. Whenever the radius becomes equal to the radius of the D, the charged particle will come out, and it is coming out with increased speed. So, as the speed increase, I can say that it is getting accelerated. Now, the radius R is equal to, I can say that mv divided by bq. And what is the time period of revolution? R being the radius, and here the time period of revolution, as we discussed in the previous topic, time period of revolution is equal to 2 pi m by bq. So time period is independent of the speed, while the radius will depend upon the speed. So the speed can be altered only by the electric field, whereas the direction of the velocity is changed by the magnetic field. Here magnetic field is changing the direction of velocity, while the electric field is increasing the speed. Because of that one, what happens means, though it starts with a small radius, the radius keep on increases. Once the radius of the circular path is equal to the radius of the d, through the deflecting plate it will come out of the cyclotron. This entire experimental setup will be kept inside an evacuated chamber. This entire experimental setup will be kept inside an evacuated chamber. Why it has to keep inside an evacuated chamber means, if there is some air present inside this chamber, what is going to happen means, these charged particles will interact with the atoms of that air molecules, and because of that interactions we will be having some other radiations will be there, as well as some other kinds of ions will also be produced. Therefore, here our requirement is only we have to accelerate the given charged particles. Therefore, we have to evacuate this complete experimental setup. Therefore, it is enclosed. This cyclotron is enclosed inside an evacuated chamber. Here these two are said to be Ds. Why? Because the shape is looking like the letter D. Therefore, we will be calling this Ds. These Ds are made up of metallic sheets, and it is a three-dimensional one, and it is made up of metallic sheet. Why it is to be made up of metallic sheet means, metal is able to shield the electric field. Electric field lines cannot pass through this metallic sheet. So in this Ds there is no electric field. There is electric field only in between the Ds. In this gap only electric field is there. And here in the Ds there will be a magnetic field, but there is no electric field. So from here to here and from here to here, magnetic force is performing some kind of work, whereas in this region electric field is performing some work. Is it clear? So electric force is able to accelerate the charge, while the magnetic field is able to change the direction of that charged particle. Finally, what you understood means, the time period of revolution t is equal to 2 pi m by bq, which says that time period of revolution of the charged particle is independent of velocity of the charged particle or kinetic energy of the charged particle. Because of the velocity, the charged particle is going to have the kinetic energy. And this term says that time period is not depending upon the kinetic energy of the charged particle or energy of the charged particle. Hence, the cyclotron is a device. As it is a device, it should work on a particular principle. Then what is the principle that is involved in the cyclotron means, the cyclotron is a device which is working on the principle that time period of revolution of the charged particle is independent of kinetic energy of the charged particle. Let me calculate the kinetic energy of the charged particle in this case. We know that R is equal to mv by bq. From this, V is equal to bqr divided by m. Now, this implies V square is equal to b square q square r square divided by m square. From this, m into V square is equal to b square q square r square divided by 1m. I brought this side, therefore only 1m will be remained. So I can also write it as half mv square is equal to b square q square r square divided by 2m. So therefore kinetic energy of the charged particle is equal to b square q square r square divided by 2m. This is the formula for kinetic energy of the charged particle. So kinetic energy depending upon what? Radius. But it is independent of what? Time period. It is independent of the time period. So time period of revolution of the charged particle is independent of the kinetic energy of the charged particle. This is the basic principle involved in the cyclotron, and cyclotron is a device which is used to accelerate the charged particles. So briefly, what is cyclotron means? Cyclotron is a device which is used to accelerate the charged particles, which will be further useful for bombarding the nucleus in order to study the structures of the nucleus. And this was designed by Lorentz and Livingston in the year 1934. The cyclotron is consisting of two metallic shaped Ds, and in between the two Ds there is a small gap will be present, and the two Ds are connected to a alternating AC source whose frequency is taken as FA, and now at the center of the disk we will be going to keep a positively charged particle. So once the charged particle is present in the electric field, it is experiencing electric force. Because of the electric force, accelerated towards another D2, and inside the D2 it is experiencing magnetic force. Therefore, it is following the circular path without any change in its magnitude. Once again, when it comes to the end of the plate, the field direction is going to be changed. The electric field direction is going to be changed with the help of the oscillator, AC oscillator. So now in the disk, the radius is remaining constant, but once it comes out of the disk, again because of increased velocity, radius is going to be increased. This is what happens in the cyclotron. And now what is the frequency means? Once you know the time period, we are able to get the frequency, because frequency is nothing but reciprocal of time period. Therefore, I can say frequency f is equal to 1 by t is equal to bq divided by 2 pi m. This is the frequency of revolution of the cyclotron. Now, I will say that cyclotron will be under resonance whenever the frequency of revolution of the charged particle is equal to the applied frequency. For resonance, what is the condition? For resonance, the applied frequency of oscillator will be equal to the frequency of the charged particle. This is the condition for resonance. What is meant by resonance? At resonance, the energy will be maximum. The energy will be maximum. Here it says that radius of that path will be maximum. So at resonance, FA should be equal to F. Here F is the frequency of revolution of the charged particle, and FA is the frequency of the oscillator. So whenever these two frequencies are matching, we will be saying that cyclotron is under resonance. We will be having the maximum kinetic energy for the charged particle. So once the energy is maximum, that energetic charged particle will be used to bombard the nuclear particles in order to study their structures. Is it clear? This is about the cyclotron. And now we will be going to discuss about the last topic for today's class, that is if the charged particles enters into the magnetic field at an angle other than 90 degrees, what is going to happen? What is the path it is going to follow? So far we studied that when a charged particle is entering into the magnetic field, normally it is following the circular path, and based on that only we have studied about the cyclotron. In cyclotron also we have taken the condition that the charge is entering into the uniform magnetic field normally. But now we are going to study the case where a charged particle is entering into the magnetic field at an angle theta other than 90 degrees. Now, what kind of path it is going to follow? That we will study here, and that is going to explain why we are having the spectacular colors like green and pink. Dancing colors of green and pink will be noticed in the Alaska and northern Canada. Why it is so can be explained using this concept. So now, let me choose this is the magnetic field, direction b bar, and a charge is entering into the magnetic field with some velocity v bar at an angle theta with the field direction. This is x axis, let me take, and this is the y axis. This is the y axis. Now here the charge is not entering into the magnetic field parallelly or perpendicularly. It is entering at an angle theta other than 0 degrees and 90 degrees. Now I can resolve the velocity vector parallel to the magnetic field and perpendicular to the magnetic field. What is this v bar in the direction of b? The v bar in the direction of b is taken as v cos theta, and this in this direction is taken as v sin theta. So here Vx is equal to x component of velocity is v cos theta, or this is the component of velocity parallel to magnetic field, and Vy is equal to v sin theta. V sin theta is the component of velocity perpendicular to magnetic field. Now as we studied previously, if this is magnetic field direction and this is velocity direction, what is the magnetic force? If b bar and v bar are parallel, magnetic force is 0. Yes or no? Now, if this is magnetic field and this is velocity, the force is maximum, and this maximum force is equal to bqv. Yes or no? These two conditions we have studied in the beginning of the class. When velocity is parallel to magnetic field, the magnetic force is 0.
it does not experience any magnetic force. When the velocity is perpendicular to magnetic field, it will experience a maximum magnetic force which is equal to BQV. Now you see here, V sin theta is perpendicular to B. This case is similar to this. So because of this vertical component or perpendicular component, it has to follow which kind of path? Because of this one, V bar cross B bar is into the board. Therefore, it will follow the circle like this. V bar is like this, B bar is like this. V bar cross B bar will be V bar upward, B bar like this. V bar cross B bar is inward. Therefore, the charged particle has to follow the circle in this way. Once a charged particle enters into the uniform magnetic field perpendicularly, it is following the circular path. Therefore, it has to follow the circular path like this. So, vertical component of velocity is responsible for the circular path. Therefore, the charged particle has to move like this. It has to follow the path like this. But now, the charged particle is also having the horizontal component of velocity. This horizontal component of velocity is not affected by the magnetic field. Therefore, because of its horizontal velocity, the charge has to move like this. Because of the magnetic force due to vertical component, it is following the circular path. Because of horizontal component, it has to come like this. Therefore, it is just like the case a spring is elongated in this direction. Therefore, the path followed by the charged particle will be spiral path or helical path. This path is said to be helical path or spiral path. Spiral path or helical path. So, whenever a charged particle enters into the magnetic field at an angle theta other than 0 degrees and 90 degrees, the path followed by the charged particle is helical. Most important in the theory questions or in 1 mark questions they will ask. When a charged particle enters into the uniform magnetic field perpendicularly, the path followed is circular. When the charged particle enters into the magnetic field at an angle theta other than 90 degrees and 0 degrees, the path is helical. So, 2 different cases are there. One is perpendicular case, the other is at an angle theta other than 0 and 90 degrees. When the charged particle is entering into the magnetic field perpendicularly, it is following the circular path. When it enters at an angle theta other than 90 degrees and 0 degrees, it is following the spiral path. Now, in this case, in this spiral path case, what is the time period of revolution? We know the time period T is equal to, we know that time period T is equal to 2 pi m by BQ. So, time period is independent of the velocity. Let me see here. Circular path is because of what? Here, when a particle moves in circle, it is experiencing centripetal force. So, centripetal force is provided by magnetic force. So, this implies mv square by r is equal to magnetic force. Magnetic force due to vertical component I have to take. Therefore, I have to take it as BQV sin theta. This implies this V and this will cancel. Then I will be writing it as mv by r is equal to BQ sin theta. This implies r is equal to this V is nothing but velocity component is V perpendicular. Therefore, I have to write it as m into V sin theta whole square divided by r. Centripetal force is because of this velocity component is V sin theta. Therefore, a V sin theta I have to take. Therefore, here I will be having one V sin theta will cancel and we are remaining with m into V sin theta divided by r is equal to BQ. This implies r is equal to mv sin theta divided by BQ, or simply I can say that r is equal to m into V perpendicular divided by BQ. Previously I told you that r is equal to mv by BQ. Here I am writing r is equal to m into V perpendicular by BQ. So, what it says means the radius is depending only on the component of velocity perpendicular to magnetic field. It is independent of the component of velocity parallel to magnetic field. So, radius of circular path is depending only on the component of velocity perpendicular to the magnetic field, but not on the component of velocity parallel to the magnetic field. Is it clear? This is the radius. So, when a charged particle enters into magnetic field at an angle theta other than 90 degrees, it is following which kind of path? Helical path. When it enters into the magnetic field perpendicularly what kind of path it is following? Circular path. Is it clear? And now I told you that in Alaska or in northern Canada we will be having the dancing colors of green and pink. Why it is happening so? So if this is our earth and this is the polar region, earth is also surrounded by, earth is treated as a bar magnet. Because of that, around the earth there is a magnetic field which is called earth's magnetic field. So at the polar regions, earth magnetic field will be directed like this. This is BE, this is BE, earth magnetic field I can take like this. Now when some charged particles coming from the outside the earth's atmosphere enters into the atmosphere of the earth, if this is a charged particle, the charged particle entering into the magnetic field of earth, because of this the charge has to experience the magnetic force. Because of this magnetic force, what should happen? It has to follow this path like this. It has to follow the helical path. The charged particle entering into the earth magnetic field has to follow the spiral path or helical path. Because of this one, the charged particle is getting accelerated. When it is accelerated, they will be bombarded with the atmospheric particles. The atmospheric particles means nothing but the oxygen and nitrogen. The earth atmosphere is consisting of oxygen and nitrogen, and other gases will also be present. When these charged particles, accelerated charged particles are bombarded with the oxygen atoms, the oxygen atoms will be excited. When they got excited, they can't stay in the excited state for more than 10 power minus 8 seconds. Therefore, they have to come down to the ground state. While they are coming down to the ground state, the oxygen will emit the green color light. Oxygen will emit green color light. In the similar way, when the charged particle bombards with the nitrogen get excited. When it is coming to the ground state, it will emit the pink color light. Pink color light. So this green and pink color lights will be seen in the sky. Generally, in our surroundings, we are not noticing green and pink color lights in the sky. But in the North Canada as well as in the Alaska, in these regions, which are the polar regions of the earth, we will be having these colors which are dancing. Why the dancing nature appears means the charged particles are following the spiral path. Due to that spiral motion, when they are interacting with the oxygen and nitrogen, they are emitting the green and pink colors in a spiral path. Because of that one, we will be having the spectacular color pattern in the sky. This is the reason which is behind the green and pink appearance of the sky in the polar region. Is it clear? So this is about the today's class. And next